Yes, good evening, everybody, and welcome to this, the first of our tech talks for this season. We're kicking off in January. We have kicked off in October before now, but we're running a bit late. I am Angus Armstrong. I organise the tech talks for CED. And if you're not already on our mailing list and you'd like to hear about these talks, then if you can email me at techtalks@ced.org.uk. So that's techtalks at ced.org.uk. Obviously, this will be recorded, and if you need to check that, you can do so later on. If you'd like to find out more about CED or to consider joining, then please visit our website, www.ced.org.uk. All of our talks are recorded and they're available on CED's website and our YouTube channel. And tonight, we are super pleased to have Jonathan Appleby and Darran Waters, and they have agreed to talk to us this evening and share the story of the refurbishment of the hydroelectric plant at Kuluva Hospital in Uganda. So I will hand over to them now. So I'm handing over to you now, Darran, so you can share screen, and I think Jonathan's going to speak first.
Okay, thanks, Angus.
So if you just hold a second there, Jonathan, I'm just going to pin you. No, I don't know whether I need to pin Darran as well, so I'm just going to do that. Okay.
Can you all see the screen okay?
I can certainly see the screen.
Good, right, okay. And if you've got any problems hearing my voice or Darran's, just, I don't know, you'll have to put something in the chat or something like that. So this is a talk about the refurbishment of the hydropower scheme at Kuluva Hospital. We're pitching this talk as if we're talking to people that have got some sort of engineering background, but not necessarily much knowledge of hydropower as such. So thanks, Edward. Yeah, so apologies if there's stuff you don't understand, and by all means ask away at the end. So Kuluva Hospital, just to put you in the picture, is in northwest Uganda. Some 8, 9, 10 hours drive from Kampala. I won't say much about the hospital itself. It's an ex-mission hospital. It's run by the Church of Uganda with support from overseas agencies that have funded this over the years. Could we have the next slide, please, Darran? Yeah, so this is the outline of the talk. Just a bit of background about the actual, about the hydropower scheme. Few slides on that, and then the problems that were identified with the scheme. Then a little bit about, well, what it says, they're creating a sustainable structure. That's organizationally speaking, a sustainable structure. We'll say more about that when we get to slide 15. And then we move on to the actual, how we've solved at least some of the engineering issues and the lessons that we've learned along the way, especially in this last year, in October 2024, and also in March when we visited the site. And then we'll summarize and talk about, just very briefly, about further work that's needed, and hopefully there'll be time for questions. Okay, next slide, please. Right, so the history of the system: it was commissioned in 1995 by German engineers using German equipment. This is the intake pond. So there's a river feeds this pond, and you can see there that there's an overflow weir, so the excess water goes back down into the river. And at the other end of the pond, probably you may be able to see it, is an intake chamber. Next slide, and that is a slide of the intake chamber with the sluice gates opened in the dam so that the water levels dropped. And you can maybe see, as an aside, that there's a lot of silt trapped in this dam. And that is one of the major problems. We'll return to that later on. So that's where the water from the pond goes into this intake chamber. And from there, it goes into a steel pipe. Next slide, please. Which is 1,200 meters long, 400 mil diameter, steel. It probably was coated at some point in the past, but that's long since gone. And it's, every so often there's flange joints there, you can see. And that particular photo shows scour point. It was a low point in the pipeline, which we'll come back to later. So next, please, Darren. And at the bottom of the 1,200 meter long pipe is the powerhouse, which contains a turbine. But yeah, so that particular picture, what you can see is the powerhouse. You can see actually where those people are sitting is the tail race, which is where when the water's been through the turbine, it's come down the pipe, it's gone through the turbine, then goes out of that tail race and back into the river, which is not visible, but is immediately in front of where the photograph's taken. So that's the idea. The water returns to the river. So the powerhouse obviously contains all technical equipment. Next slide, please. Okay, Darren has very helpfully drawn as a long section through the scheme. So you can see the red line being the steel pipeline. You've got the intake pond, top left. The pipeline going down, there's a low point. There's a little high point where there's an air valve. And then the pipe drops again to the powerhouse itself. And then the wastewater, if you like, returns to the watercourse. And you've got the turbine inside the powerhouse. So that gives you some idea of the distances. You've got 1,200 meters length, and the height drop is about 80 meters from the intake down to the powerhouse, which is that 80 meters is what gives you the driving head to power the system. Next one, please, Darren. And that's a photo inside the powerhouse as it was before it was refurbished. So on the right, the orange thing on the bottom right is the Ossberger cross-flow turbine from 1995. You can see a flywheel. Yes, Darren's highlighting with the mouse there, a whopping great lump of steel that rotates very rapidly. And behind that, not very easily visible, is the generator, which converts the rotational energy into electricity, which is what we're wanting to get. And then at the back of the room, you can see two control panels. Well, one control panel on the right to control the turbine and how it's operated. And then the panels on the left are dealing with the high voltage electricity and the routing of it in the right direction. So we didn't actually touch that bit during the refurbishment. We left those two cabinets on the left. They're about one of the few things that stayed put. In the foreground is a red valve, which is supposed to isolate the flow of water. So you switch the valve off, in theory, no water comes down the pipe. We soon found that doesn't actually isolate the water. And that's one of the problems. And then the orange thing towards the left is called a hydraulic power pack. And it wasn't working very well, so it needed replacing. So that's basically the existing system. Oh yes, and on the outside of the building, you've got a transformer. So the electricity generated is transformed to a 6 kilovolts, 6,000 volts, and went out in a buried line, which is 1,750 meters long, to get to the hospital. Okay, next slide, please. And one of the problems, or perhaps take a step back first of all. The thing that happened first, really, in CED's involvement was a visit by John O'Cox, who I think is listening into this presentation. Jono visited in March 2020, had a good look at this system, and wrote a very detailed report, which and then he enabled several problems to be identified with the scheme. And it was Jono's report that effectively was the blueprint for what happened after that. He sort of identified the issues, and we then set about solving them over the next 3-4 years. One of the problems was this buried high voltage power line, which had a habit of burning out and being eaten by termites, and that's a picture of a damaged underground cable. So that was a major issue, and it was decided to solve that by making it an overhead line instead of a buried line. So that was one of the things that needed to be done. We'll come back to that. Next one, Darran, please. Another problem that Jono identified is the very high silt load in the river. It does carry an awful lot of silt down with it, and that settles out in this pond. But once the pond's filled with silt, what happens is the excess silt then carries over into the intake chamber down the pipeline and merrily destroys the runner, the turbine itself. So that's a problem that we had to try and solve. Next slide, please. Oh, there you go. So the silt load over the 29 years since the turbine was installed caused the damage with this is the runner. This is the bit that revolves, that the water hits and turns very rapidly to create the electricity, to generate the electricity. So this is, as you can see, been very badly damaged over the years and just worn away. It may also have been hit by some stones from time to time, looking at it. And it was worn to the point where it was decided to replace it with a brand new one. It wasn't really repairable. Next slide, please. Another issue that was identified as losses in the pipe, caused partly, at least, by encrustation in the pipe. And that's a photograph looking up the pipe from the bottom. And you can see that that actually a lot of it is caused by corrosion of the steel, forming corrosion nodules. And inside the nodules, there's pitting corrosion, which is merrily eating away at the pipe, and over time will start to cause major leaks. So that's an issue that needs dealing with. Next slide. And yeah, it's one of the main issues, I think, over the years was lack of maintenance. Faults, when they occurred, were often left unrepaired or just bodged a little bit. And the line behind that is the fact that the hospital never had any money for that sort of thing. The money is very tight, and in these mission hospitals, there's never enough funds for whatever they want to do. So, you know, if somebody comes along saying, "Oh, I need a few £1,000s to repair this," it doesn't always get done. And that's what has happened. You know, the cleaning of the dam hadn't happened very often, so the silt had carried down the pipe. Parts had become faulty and had not been replaced in the powerhouse. The isolating valve was down in the powerhouse was leaking, but couldn't be replaced because of lack of money, and so on and so forth. So that's a major issue. Next slide, please. One of the things that Jono recommended in his report, and one of the first things that they did at Kuluva, was in fact to create a special purpose vehicle, a company specifically to run the hydro installation. From then on, and they've created a board, they've got directors, and so what they're trying to do, they're doing is isolating it as an entity from the hospital, and over time creating an environment whereby it can actually generate some income as well. One of the things that can happen now that the refurbishment has happened, one of the things that can happen is that we can sell electricity, because we've now got surplus. We can sell it to neighboring or neighbors of the hospital. and generate income. So we're trying to create a company that is sustainable, with the idea that money will can be raised and used for maintenance in the future. Okay. 2022, we made a return visit with Johnny Burns, who was here. You want to try clicking that to see if it works, Darren? De-silting, this time using mechanized equipment. You can see how big a problem the silt is in this behind this dam. It's a bit glitchy is the video, but you've got the idea anyway. So that's one way of de-silting the settling pond, is to get in a big excavator and do it that way. We tried that in 2022. Next slide, please. In 2023, with the help of Paul Darrell, another CED member, and some advice again from John O'Cox, we put in an overhead line. So that's a photo of the new overhead line replacing the buried line. So that solved the problem of burnout of joints in the buried cable. That was one important step on the road to recovery of the scheme. Next slide, please. The powerhouse itself needed some repairs to its structure, and that's a picture of them re-roofing it. Ignore the health and safety violations. Next slide, please. And it had actually been some subsidence to one corner of the powerhouse, so we eventually managed to do some underpinning work to stabilize the corner where there was some settlement occurring. And moving now into 2024, it's just this last year, we wanted to be able to clean the pipe, a process called pigging, where you pass a foam pig or a foam, well, yeah, just a big swab, if you like, a foam swab down the pipeline. But you need somewhere to collect the pig at the bottom of the pipeline. So we had to construct a pigging chamber, which we chose at the time to site it at the lowest point of the pipe. So this is us constructing the pigging chamber, which has to have quite a bit of concrete in it, because it's got to be able to hold the pipeline in place with quite a lot of force acting on the pipe. So we're constructing it around the low point in the pipe. Next one, please. Yeah, another photo of showing them fixing reinforcement bars and a wall on at either end of the chamber to hold the pipe in place. Next slide, please. Completed, well, not the completed pigging chamber because the roof's not on yet, but you can see how it's now surrounded the pipe. And we need to have a removable section in the pigging chamber so that we can take the pig out when it arrives there. Having put the pig in at the top of the system, you need to be able to take it out at the bottom here. Next slide. That's then cutting out of it. Getting people with sufficiently good welding ability in this part of Uganda is not easy. So it took quite a bit of searching before we found people that were competent to do this job. And even then we had to keep a very close eye on what they were doing. Next slide, please. This is in March 2024. And Trevor, I don't know if Trevor's here tonight, but Trevor Burns was with me on this visit. And this is our first pigging. I'm not going to go into pigging in too great detail, but we've put the foam pig in at the top of the pipe. It's come up, it's shot all the way down to this point and has arrived in the blue section at the bottom there. And we're now just releasing the pressure behind it by opening a valve. And you can see all the dirty water that's shooting out towards the watercourse away off picture. So pigging can be quite an exciting process, especially if you haven't adequately catered for all the forces involved. But it went well, that process. Yeah, so this next slide, there had been an air valve at the high point in the pipe, which was open continuously and spraying water everywhere, which is good for the local farmer, but not good for the hydro scheme. So on the right, you see the new air valve with a protected cage to stop it getting tampered with. That was installed late 2024. So next slide. And I think this is the point where I can hand over to Darran for a few minutes, and you can do some talking.
Oh, so yeah, this was in October 24, as it says, and a different means of cleaning out the intake pond. So we managed to, or the guys managed to get about 20 or 30 guys from a local church who they could pay to clean out the pond. And this silt then was taken down through the penstock and into the watercourse and taken away. So it didn't need the excavator. The other thing with doing it this way is it takes longer, but we had the pipeline closed anyway, so that was good. You can also see the rock that the dam is built on there. So with it drained down, you can see the rock. But yeah, they're making good headway clearing out that silt to avoid it going down the pipeline. There you are. So this is the completed pigging chamber 6 months later. So we were able to pig it again. But this time, Jonathan brought a abrasive pig. There's a picture of that now. So the picture on the left, Jonathan's giving a bit of a toolbox talk at the beginning of the day as to what we were going to do. You can see the old pig, just the foam pig there, and this one is the same, but it's covered with a very durable plastic, rubbery plastic, but with a sort of carborundum sandpaper type finish. So that was deliberately to knock off some of the nodules that Jonathan was talking about on the inside of the pipe, where the corrosion was happening underneath. So to knock off the top would slow down the corrosion anyway, where the pits were. And this is the intake chamber. You can see the plate that they're lifting up. At the lower part of the plate, there's a grid. So I think it's 16 mil by 16 mil to stop stones bigger than that and any trash and debris going down the pipeline. So this is pigging in operation again. I've got audio on my side, so I'm trying to speak over it. But this was just before the pig came into the pigging chamber. The color of the flow changes from fairly clear to very dirty, and you know the pig's about to arrive. And then just shortly after, you hear a thud, and the pig is there. So then we have to drain down the water flow that was used to push the pig to this point down. There's another video here. So once the pig has arrived down at the bottom, we open up the bigger valve and let the flow of water that's behind the pig, and again, very dirty water. And once it stops, you can see all the bits of metal that have come off the pipe, which we'll see in a minute. So yeah, on the left-hand side, you can see all the sort of tops of the blisters that have come from the pipe. So the pig did a really good job of knocking off the nodules. You can also see how we took out the pig there from needed a bit of gentle persuasion to pull it out. It's a nice tight fit in the pipe. So the pipe was unbolted, both the flange on the front and from the main pipeline. And then there's Jonathan just pulling it out. So this is a shot up the pipe once we pigged it, and you can see in the top left, that's the sort of size of the typical bits that came off from the blisters, and then you can see how many there were on the pipe. And how it's done really quite a good job. So important that the pigging is done regularly so that these nodules don't keep growing. So that's the pitting corrosion. And that's it all put back together again. Bottom right, you can see the dismantling joint being put back in. This is relatively easy, but it's being used with the bit of a tree there that they managed to find to lever it up into place. So so yeah, that's that put back in operation. So down at the turbine at the powerhouse, you can see what we've got there. What was really good about this, and one of the good points to make a note of, is the paving that we see in front of it. That wasn't there before the project started. So just before they paved this area, which was a real benefit to us, because we had to use trolley jacks and pallet trucks and all sorts to lift things across from the storage unit, which is where I'm taking the picture from, to the powerhouse. And to the side of the powerhouse, you can see the flow meter chamber. Also, we had lots of nice tools that Luke bought for the project, and the guys were all very keen to use these tools. So each morning we'd have a health and safety talk, and just remind them to use the right tools for the job and always to use PPE. It was really quite impressive, actually. I didn't have very high expectations when I came out as far as health and safety, but we had the site, you can see the yellow around the site. We had it sort of cordoned off, and toolbox talks every morning. So so we tried to keep as safe as we could. So I'll go on to the next slide. So one of the things that Jonathan mentioned was the main inlet valve was leaking. So we wanted to try and refurbish it. So that's what we did. We took it apart, had a look at what the problem was. We thought perhaps that in the bottom there might have been some firm silt that had gone hard, stopping it from closing properly, but that wasn't the case. And you can just about see it was scored down the sides. So there was a number of places where there was scoring on the gate itself, the rubber coated gate, and on both sides. And then there was broken parts on the groove on the housing that fitted into the groove. So we didn't know what to do about it, and in the end we decided to build it up with some epoxy resin, which is what we did, a number of coats and sanding between coats, and then painted it back. And then reassembled it. Unfortunately, it didn't solve the problem completely, but at least we know that we can't solve the problem. So there's we probably improved it, but it's still leaking, sadly. So there's but we know that we're not going to solve it. Another one of the problems we had was putting the panel in to the building. We managed to get it with the fork truck, as you can see in the bottom right, but you can see the size. It's only inches smaller than the opening we had to get in through. And immediately when we went in, we had to turn it through 90 degrees in the direction that you can see in the main picture. So it was very heavy and very difficult. I'll just show you this picture now. Sorry, the video. So it was quite a lot of work, an effort to pull that in. There was 4 or 5 of us on one side and 4 or 5 pulling from the front with straps. We had to build up platforms with timber and used sort of coated MDF to make it slide as easily as possible. So yeah, it was quite hard work, and we were all quite pleased with ourselves once it got in that far. And it stayed there for a few days before we had the energy to think about getting it into its final base. Which there it is. It's in its final place above the cable trench underneath it. So that was another problem, was turning it around and pushing it into position. and you can see inside the switchgear, which is the existing switchgear here. There was a slight repair we had to make in the mechanism, which wasn't working. So the guys made some new parts which had worn out, so that the switchgear tripped when you opened the door. So you could isolate it when you opened the door, rather than by putting your hand inside and operating it like it was. So I mentioned the flow meter chamber. This is the flow meter chamber just up in front of the powerhouse. And the purpose of the flow meter chamber is to expose a section of pipe. And it's to expose the section of pipe. So this is inside the chamber now. And this are some ultrasonic sensors on the outside of the pipe, so they can record the speed of the flow inside the pipe. So they measure velocity based on the distance apart and the internal diameter. So that was fitted to the pipe, and the cabling put through into the main powerhouse building. And that's a picture of Johnson, who was proud of his cabling and the control unit there on the wall. So this is another shot showing everything out before we reinstalled the new equipment. Quite a lot of work had to take place inside the building. The trenches that were there before for the cables and the hoses weren't necessarily in the right position, so we had to make some modifications, and this picture just should, when I let it go, show Johnson at work, and you can see he's wearing his all his PPE, and everyone else is out of the building because it's quite dusty. So that's one. It's another video here. I'm sorry you can't hear the sound. I don't think it's working. So there's lifting beams in the building, but the lifting beams are above the main kit, so above the flywheel, above the generator, and above the turbine, and so they're not much use for lifting things that aren't underneath it. There you are. There's the new hydraulic power pack being installed into the building, and the power pack is primarily we'll come to that in a minute. It's primarily for controlling the vane on the turbine. So here's the turbine. So it's just being lowered into place, and we had a few teething issues initially with the bolt holes. So it was an Ossberger crossflow turbine that was ordered from the manufacturers of the previous orange one. And we hoped that the holes would be in exactly the same position and it would fit exactly as it should. You can see from this picture, we got two fixed points here, and this has to be exactly, the shaft has to exactly line up with the flywheel. Jonathan will talk a bit more about that in a minute. So we didn't have much tolerance, so that the holes needed to be in exactly the right position. So we had to file some of the holes just to make them with enough tolerance. And you can see at the bottom, compared to that picture that Jonathan showed earlier with the pitted runners, how much better that one is, and it really makes you realize that it needed replacing. So I think it's at this point I'll hand you back to Jonathan.
Okay, thanks, Darren. Should also say something about the team at Kuluva. There's Dr. Luke Voss, who's the other Mzungu that you've perhaps seen in some of the pictures. He's a medical doctor, and although he's not an engineer, he's got a good knowledge of engineering that he's picked up, and he is primarily the person that's been responsible for raising the funds for this project, which is cost in the region of about £200,000 when you counted it all up, and he's raised that from his through his contacts in Australia. He's from Australia. But we've also got a good local team there. James Jogo is a project manager. You've seen Johnson in the pictures as Nelson, and the names momentarily escapes me of the other ones. But anyway, there's several guys. It's a team effort, and they all did a really good job and worked really hard.
There's a picture of them at the end. So
oh yes, we'll see that at the end. Thanks, Darren. Yeah. So yes, and the turbine, the new blue turbine, is supposed to be an exact copy of the old orange one, from the same manufacturers in Germany. It was made there in 2023, and then was shipped, and took an awful long time to arrive. It only arrived in Kuluva in August of last year. But you know, that's just what happens. These things take a long time to manufacture and then get shipped out. But finally, we got it here at Kuluva, and yes, so we're trying to get that blue thing lined up to the flywheel generator axis that is on towards the right of the picture, and it has to be to within 0.4 millimeters horizontally and vertically alignment to that flywheel axis, and that creates a problem. Not so much the alignment itself, but the fact that if you get that lined up with the flywheel, it doesn't line up very well with the red valve on the left of the picture, which causes a lot of problems, and we've learned a lot from that. Anyway, next photo, please. So to get that new blue turbine aligned, you can see at the bottom right of the picture, as the turbine there, you can see the flywheel at the back of the page, the back of the picture. You have to use some dial gauges and rotate the flywheel round. So as you're rotating the flywheel shaft, you're measuring the out of position, if you like, on the new turbine shaft, and you just keep doing that until and okay, you take several readings. You say, oh no, it's far out. We'll have to find something to change the position of it. So we ended up putting little plastic and rubber, steel bits of steel here, there, and everywhere, just to get the turbine correctly to level. Next slide, please. That photo was taken. I think we got it pretty much in position. We got it pretty much lined up as we wanted it to be lined up. So it was correctly aligned, and then we were tightening up this black, what we call the transition piece that you can see there in the picture, connecting that up to that red valve that's off the picture, and trying to get it to seal at each of those two joints. And we thought we'd done a good job. And then the engineer arrived from Ossberger, and we got to the stage where we could pressurize it and actually put water into that pipe. We suddenly found there was water coming out of the joint, which is the joint between the black transition piece and the red valve that you can't see in this picture. Perhaps if you go to the next slide, Darren. There you go. Yeah. So that was the joint. We couldn't get that to seal. So we sent our was it Helmut? Oh, Gunther, that was his name, Gunther. He was sent Gunther back to his hotel, our commissioning engineer from Germany. He went back to his hotel, and we worked on into the evening to replace this gasket with a better one, although actually we didn't do such a good job as we thought we were doing. And we got it all back together again for the next day, pressurized the system, and it kind of held, but that gasket that you can see, sort of cream colored thing, it held for most of the next day, and then it blew at about 4 o'clock and showered us all with water, and we had to shut the system down again, send Gunther back to his hotel for another early night. And if you go to the next slide, Darren, we had to manufacture a gas, kind of a restraining strap to hold the gasket in place just temporarily, so we could get the commissioning done. So there's Letty, car mechanic, doing fabricating a gasket repair strap. Next slide, please. And that's it in place at about 11 o'clock at night. You can see basically it's something that clamps around the flange and just forces a piece of steel into where the gasket had blown. And it worked, actually, and it's still working. There's a more permanent repair that's ready to be installed, but at the moment, this is what's still holding the pressure and keeping the powerhouse free of water, this temporary repair. Next slide, please. So the next day, Gunther was able to come back and finish commissioning. He'd come out from Germany for a 4 or 5 day slot to do the commissioning. And the rest of the time that he was there was spent in training staff, because obviously they've got to be able to operate it when he's gone back. Is that a video? Yeah, it's not that you can hear it, but you can at least see the flywheel spinning away there. So at that point, it's actually putting electricity into the local grid and back up to the powerhouse. Next slide, please. Oh yeah, you can see it. Yeah, so that's the readouts on the control panel there, just telling us at that point it was only generating 15 kilowatts, but that's fine. So it's capable of generating, we think, probably a good 100 kilowatts at full power. The hospital doesn't need 100 kilowatts. It needs more like between 30 and 50. And so the excess can be sold. And we already have 1 or 2 institutions that are going to be buying, or already are buying electricity from this scheme, which generates revenue for the hospital. And there's a university campus down the road that is hopefully going to also sign up and add to that revenue stream for the hospital. So as well as supplying the hospital, we're also hopefully created a sustainable solution where the revenue is going to pay for maintenance in the future. Because as you can appreciate, a system like this doesn't run without maintenance. You've got to keep on top of it, of maintenance. Otherwise, it'll go the same way as the old scheme. Next slide, please. And yeah, a photo that Darran took of the staff, the crew that was assembled. It was quite a few guys, but you need a lot of folk doing stuff to make something like this happen. And some of the ward staff. Presumably you took that, Darran, on our trip around the hospital wards. We were given a guided tour to see what was going on in the hospital itself. Right, where have we got to? I think that's, yes, further work remaining. Thank you, Darran. That's we've realized that we need to do more. So although we've done the main bit of work, there are still some things which we could improve on. There is the issue of sediment or silt at the intake. It might be possible to design a continuous system where silt is continuously flushed away from the intake, and that's what John O'Cox may be able to help us. He's listening into this presentation, I think. So that's one big item that we need to work on. We need to consider whether we can do something to stop further corrosion happening in the pipeline, possibly cathodic protection. We need to install lightning protection. That's actually pretty much ready to be installed, and it's very much needed there. We witnessed several major lightning events whilst we were there. We can attest to its necessity. And then possibly building on the fact that we learned that actually having that MIV and black transition piece perhaps we could have, we should have installed a dismantling joint in that and renewed the MIV, or possibly we could do that in the future. So that's something to consider as well. And then fifth point there, yeah, do we need to have additional pigging provision just upstream of the powerhouse? So as you can see, there's other things that could be done to improve it. And yeah, that's still to be thought about and discussed and decided. Any questions? I think that's it. Darren, do you want to add anything before we open it for questions?
No, I don't think so. I think it's probably just one thing that we didn't manage to pig the section from the pigging chamber down to the powerhouse. So that section hasn't been pigged. And so it would be good if we could come up with something that would allow that to be pigged in the future.
Yeah. Mm-hmm. Yeah. So if there's any questions, I'm aware we've flown through.
Well, you've just answered one of my questions, which was going to be the bottom 400. Did you say 400 meters? So you've effectively pigged 2/3 of it, and presumably the bottom third is as corroded and as clarted up as the top of it.
Yeah.
So you could significantly improve things by a second pigging chamber, and presumably the pig couldn't sort of swoosh through the low point up and over and down to the bottom.
Well, possibly it could actually, and that's maybe where we're thinking about it. We may have missed a trick earlier on, and at the time when we were making decisions about this, we thought the pig had to be at that low point rather than at the powerhouse because we didn't have the space at the powerhouse.
Right.
If I was to do it again, I might do it differently.
Yeah. But then presumably if the pig were to get stuck halfway down, it would just be dreadful.
Yes.
Have you ever experienced that, Jonathan?
No. Yes, there have been times where it's been quite difficult to get the pig to go all the way through a pipe. Yeah. It's always been solvable.
Yes.
I don't know if John O'Cox wants to add anything to the discussion. Probably got a whole load of things.
Now, Jono will be on mute. I'll just go and find John O'Cox. I've just asked you, Jono, to unmute yourself. So if you do so,
Yes.
There we are.
Thank you. Can you hear me all right?
Mm-hmm.
I can.
You can. Great. Okay. Well, first of all, to say, having been out to Kuluva, Jonathan and Darran and the local team led by Dr. Luke Voss have done an incredible job, actually, a fantastic job to achieve all that has been achieved. There's a huge number of details, and it's Jonathan has been very what's the word? Hasn't really described how difficult working in that part of Uganda can be. So a huge amount has been achieved. The idea from the early stage was there were some urgent things that needed to have been done. They've been done. Some things for the short term, medium term, and long term, and most of the urgent ones and short term ones have been completed. Just to add a point on the funding, Jonathan was mentioning that Dr. Luke Voss, got funding from Australia. I think it is worth saying that the funding, I think, came from Frontier Australia. Certainly the first tranche came from them, and we as CED we were asked to vet the application that Luke made, which we did, and so a note in passing, Jonathan, I think it would be good to make sure, even though we're not directly involved, that Frontier are aware of what has been achieved, because I think their money has been well spent, notwithstanding the outstanding items that hopefully we can cover off in the next several years. So that's worth noting. Yeah, I mean, I could talk another 45 minutes. So I should probably just shut up. I don't have I have lots of questions, but some of are already in process by email and so on. It was lovely to meet up with Darran in the service station between Cardiff and Bristol, where before Darran went out. Delighted to see that the flowmeter was installed. And to note in passing that the very tuberculated bore of the pipe in that region will possibly mean that the readings are not quite as accurate as we would like. Yes, I think pigging down to the outside the powerhouse will tax us, but it will be well worth doing that. The cathodic protection is something we need to look at. We might need to look at other ways of protecting the bore of the pipe. And the slotted pipe sediment sluicer, I think this has been demonstrated in Rwanda at for a micro hydro scheme there, and I think it could make, if we can get the design right, and there will be challenges, I think it could make a tremendous, it could be tremendously effective at Kuluva.
Thank you, John, for those thoughts. Yeah, that's helpful.
Just, I know everybody else is muted, but in the chat box down at the bottom, if you click chat, you can add a question there. Well, rather than unmuting everybody, which might become a bit unwieldy, if anybody does have a question, they'd like to stick it in the chat box, that would be great. As we were going along, I was thinking of all sorts of questions I wanted to answer, and the only one I wrote down was pigging the bottom 400 meters. We've got a new message here from Graham. What kind of surge protection are you using?
None, in the sense of, well, surge protection is provided simply by the fact that nothing can be done very quickly. And so it takes a long time, for instance, to open that valve, that red valve. It takes, even working flat out, it takes 2-3 minutes to get it open. So there is a limit to how quickly you can change the flow in the pipeline, and therefore surge isn't an issue because of that.
Might just be saying, Jonathan, why you might want surge protection. In other words, talk about water hammer a bit.
Well, yeah, I mean, you do need surge protection in a lot of hydro situations, but not all. And most of the schemes I put in Scotland haven't had specific surge protection.
Some of our audience might not understand why you might need it. You don't just switch the water off and that's fine. Just turn the tap off.
Yeah, it's basic pressure fluctuations caused by if you're trying to change the speed at which a column of water is moving. Obviously, that column of water can weigh an awful lot. It has a lot of mass. If you try and change what it does too quickly, you end up with a pressure wave being generated. Sometimes very, very high pressures being caused. So you've got to be careful. Yeah. John, do you want
I might add a comment on it. So yes, I mean, with that steel pipeline, if it were possible to close the guide vane very quickly, which the control system does not permit, then you would get a very sharp shock wave going up that pipe because it's made of steel. The size, the quantum of the shock wave is would be higher. But if those of you who remember your Joulski equation, it's the celerity, the speed of the shock wave divided by gravity multiplied by the change in velocity in the flow. That is the head rise, or the pressure head that you will see. Because the underlying pressure, because it's only, I think, 80 meters of head, the surge, the water hammer is on top of that. So because the change in velocity, because the guide vane can only open and close fairly slowly, it means that those surcharges, those extra pressures, are relatively small, and the system doesn't need any surge chamber as such. For a microhydro scheme of this sort, you can generally get away with that one. But the key is that Jonathan was mentioning the MIV valve. That's probably 20, 30, 40, 50 turns to open or close it. But it's the hydraulic power pack and how quickly the guide vanes can be adjusted.
Great, thank you very much. A couple of other questions coming in. Alan Chadbourne asks, does the pig rotate as it travels? And if so, what makes it do so?
Yes, it probably does with the bigger, the more recent pig. Yes, it probably does rotate. Mainly just because of the surface, the way that the carbide surface has been wrapped around the pig.
Mhm.
Some of them are designed to rotate, but I think probably most of them do anyway, just by nature of hitting something or passing through something. You'll know more about that, John, than I do.
The pig, yeah. I mean, well, again, Jonathan's been brave enough to actually pick that pipe, and that's fantastic. I don't know. I guess some might rotate, but if I could just go back to the question on surge from Graham Miller, it is what I thought. He was asking about electrical surges
Right.
on the overhead line, I guess. Now, I understand, and Paul Darrell would be the one to double check, but I think there are lightning surge protectors on the ends of those, what's now an above ground overhead line. So I think there are surge protectors there. I'm pretty sure of that.
Yeah, I think you're right.
Ian's asking, what pushes the pig through the pipe?
Yeah, it's just water pressure.
80 meters of water pressure is a fair old.
Yeah, you don't need to fill 80 meters. You can just once you put the pig in at the top of the intake chamber, you let that intake chamber fill it with water, and allow. Well, it depends on how you're doing it, but I was allowing, I think, 3 or 4 minutes worth of water. Once the pig had started to disappear down the plug hole, so to speak, you just let another 3 or 4 minutes of water go in after it, and then you shut off the pen stop so no more water can get in. So you're not having too high a pressure water going behind the pig, but you need enough water to flush all the rubbish out that's been dislodged by the pig. Any other questions?
Well, Nigel's asking about the alignment of the turbine and generator. I think what he's saying is, so you were aligning it left, right, up, down.
Yeah.
I think he's saying, did you also have to align it longitudinally, back and forth?
Yes, there is a tolerance for that as well. It's got to be, had to be between 3 and 8 millimeters of a gap between the two halves of the flexible coupling.
So it wasn't.
It ended up with 6 millimeters in our case.
Yeah, it wasn't as difficult as the 0.4 of a millimeter.
0.4 was the difficult one.
It's a tricky one. Yeah. Okay. Okay. So I think we've addressed the lightning and solar surge protection on the power lines, have we?
I think,
Yes, I think so.
Yes.
yeah, the lightning protection is definitely going to be happening quite soon.
Yes, I mean on the lightning protection, what it will amount to is using the CED design from Luamba Hospital in the DRC to roll up something similar to protect the powerhouse at Kuluva. It will depend on funding a little bit. Really, all the parts needed for which include a lightning rod that's on on some sort of mast, and then you need a copper strap, and then an earthing grid. Ideally we would do ground resistivity checks for the soil, and you would design it that way, but the prevalence of lightning in West Nile is probably not too far, as it's not quite as bad, but it's not far off what they get at Luamba. So we are waiting for Dr. Luke Voss, who's currently in Australia, to advise on, I guess, how he wants to, what's possible in terms of procuring bits of the system to make it as good as can be.
Okay. Well, from a very crude point of view, you've got a great big pipe buried in the ground, or at least partly buried in the ground. Does that not just do its own thing?
Yeah, I mean, generally with steel pipes, you would actually connect them to an earth for safety.
Mhm.
If some, but with a lightning system, what we're trying to do is we're trying to attract the lightning,
Ah,
which might otherwise hit and damage the powerhouse and anybody standing anywhere near it,
okay.
and to feed all that energy down a very easy channel. The easy channel for it is a big, thick cross-sectional area, bit of copper,
Yeah.
and the power will just surge through that at lightning speed, if you excuse the pun.
Mhm.
But you need to dissipate that into the ground, and where you dissipate that into the ground needs to be away from where animals or indeed humans might be standing, because such is the energy in a lightning strike that you get what's called, if you get enough of what's called a step potential, um, lightning could go up one person's leg, through their heart and down the other, and or an animal, and cause a fatality. So actually, Jonathan and Darren, one of the things we need to emphasize is that wherever the grid is, that's the underground bit, that's fenced off, if possible, in a way that it stays fenced off. So yeah. But if we
Those
have
are,
any,
those are really excellent.
lightning protection experts in CED, any new starters, then it would be really good to know. Yeah, that's sort of specialist skill. If we have people, because at Luamba they had fatalities. It's a really, really serious problem, lightning strikes. And Jonathan and Darren have experienced something of the power in a storm on their visit.
Mm.
Um, and this is maybe somewhere where we as CED, we can help get appropriate designs that are not too expensive but appropriate for the task.
Thank you, John. I think we've got one more question, which is an interesting one. Richard Francis asking, will CED have an ongoing technical advisory brief to support the Kuluva Hydro, so they can always get answers to any challenges which arise?
Yes, very good question. That I would be in favour of something like that. Up until now, the focus has been on doing the refurbishment, but now we need to turn our attention to thinking longer term. And I think that they'll be very keen to have something like that, because they seem to have got the right mindset now at Kuluva. Yeah, I think they'll be very happy to have something like that, and I certainly would like to see CED supporting
Yeah,
them. Yeah,
I
going
mean,
forward.
one thing to add to that is trying to link up Kuluva Hospital. Well, the folks in the company they've set up to operate and manage it, with their equivalent staff at Kisizi Hospital, because they also have they also have an Ossberger turbine, which they run pretty well, and they're pretty resourceful down there. They've over their time they've had powerhouse floods, they've had generators that go bang, they've had any number of fairly major project problems which they've managed to solve. So I'm very keen to try and link up with Kisizi, and indeed possibly with other um, Ugandan operators, so that they start to work together and collaborate, and in terms of keeping their schemes running properly. Yeah.
Yeah, that would be helpful.
Okay. Well, time's marching on, and I think we've not got we seem to have, we had a run of questions, but I think we've run through them. People have been very appreciative of the answers you've given. So I think we will wrap this up. I think, you know, your presentation has been excellent. The pictures you've given us have been really good. Your descriptions, your explanations have been great. All I sort of conclude is that if I could have my career again, I'd go and be a hydro engineer. It looks like a load of fun, but I've always loved hydro, having grown up in the Highland Glens and been surrounded by hydroelectric projects. So the actual outcome of the project is reliable power source to the hospital. I mean, let's not lose sight of that very human side of it, which, you know, it's just wonderful. And if do manage to generate some extra money out of it, all the better to maintain it, and you know, the surplus funds then to contribute to supporting the hospital. So all in, it's great. And I'm very proud to be part of CED and think that as part of our charity, you know, we have achieved this through an awful lot of hard work from Jono and Darran and Jonathan. I know Jonathan has worked hard on this. He never seems to be in this country, and I know you've put a tremendous amount of time in, and the same for the others. So so thank you very much. I suspect
Eddie's trying to say something.
Eddie's got a question.
Eddie's muted. Eddie, can you type?
Something. Not sure how to unmute him.
Yeah, okay. Where's he gone? I've lost you.
Oh, wait a minute.
Right, Eddie, you're live.
You hear me now? Yeah. Right, I didn't have a question, even though I had done a hydropower on and off over the years. I'd really more a statement of how I personally are so pleased that CED has been involved in a micro hydro project. As the former chairman of CED, or one of the former chairmans, I always wished that I could get such a higher tech scheme off the ground, but unfortunately this was not to be. I only personally managed to get sufficient funds from churches for small reservoirs, solar electricity and classrooms, etc., you know, which are sort of not quite as high tech. So a personal thank you, and I think it's wonderful that CED is going in that direction. I'm involved with the Canal Trust, and we do have a small hydroelectric schemes from time to time. Jonathan would be interested in this. We have one at Melksham on the River Avon that I've dabbled in a few times, but hadn't really got off the ground, but something may happen there. But anyway, that's something in this country. It's difficult enough getting something done in this country, and I can imagine it's extremely difficult getting anything done in Uganda, even though, you know, it must be much improved on the situation of, you know, 20 years ago when there were so few local people, you know, with the skills. Thank you again.
Okay. So yeah, I think with that we'll wrap things up. And I just want to thank everybody who has joined in tonight. I think we peaked at 28 people, and that's probably our best attendance for a tech talk. What I would say is that the online version gets extra views, and some of our online recordings have had very large numbers of views. So I think this will be something that a wide range of people would be pleased to refer back to in the future. So again, big thank you to Jonathan and Darran for no doubt putting in quite a lot of effort to pull that together as a talk, as well as your work in the field. So thank you very much, and thank you to everybody who's attended tonight. And yeah, all the best. So I shall. Yep. Okay. Good night, everybody.
Goodbye.
Bye.